All right, 4.1. This section is called exponential and logistic. Logistic. That's how you pronounce that second one. Not logistic, logistic. All right, so it says right here, name something that grows fast. Fast. Hurry. Something that grows fast.
Weeds.
What? Weeds. Weeds grow fast. How? Widthwise or height-wise? Height-wise. Okay. Bamboo also grows fast. Very fast. What else grows fast? Whippersnappers. Young kids. Right? They grow fast. You buy them new shoes, and then before they're worn out, they're needing new shoes again. Something you'll have to experience when you get a little older and have kids of your own. What else grows fast? Graphs. Ooh, nice. Graphs. Yeah, graphs go fast. There are lots of things that grow fast. Money. Does money grow fast? It shrinks fast. Chia pets grow fast. Right. Money growing fast is a good thing if you're earning money. It's not bad if it's like interest accruing on like a debt. That's not good. But there are a lot of things that grow fast. So polynomials that we skipped, like x squared, x cubed, x to the fourth, they grow pretty fast for large values of x. But something that grows faster than any polynomial is an exponential function. So you might hear like people out in the real world say, man, it grows exponentially, you know? And what does that mean? Why do they say that? They use it kind of as what would it be, an adverb to describe how it grows? Something grows exponentially. They're usually trying to imply that it grows what? Fast, right? Fast. But you probably wonder if those people actually sat down and quantifiably justified the exponential growth, because there is a way to justify exponential growth. And not all things that grow rapidly grow exponentially, okay? So that's what we're going to set out to do in this section. What is it to mean exponential growth, and how can we quantify it? So here's the intuitive definition of something that grows or actually decays. Like you said, money, we lose money fast. Something that decays exponentially. The intuitive definition. A quantity, whether it's money, germs, whatever, weeds, that increases or decreases exponentially will grow or decay respectively at a rate, this is important, at a rate that is proportional to the current amount. The growth rate is proportional to the current amount, or the decay rate is proportional to the current amount. To say that a little bit differently, you could say this: the more you have, the more you gain. The more you have, the more you gain. Or the less you have, the less you lose. So would weeds qualify then under that criteria? The more weeds you have, the faster they grow? Maybe not in height, right? But if you think of like weeds spreading out across like the lawn, taking over the lawn, then maybe that's true. The more weeds you have producing other weeds, and the faster they're going to grow, like sprawl across the lawn. So not necessarily the height. What about money? Would that qualify? Would money grow exponentially? The more money you have, the more money you get? It takes money to make money. If you put money into a banking account or a checking account, let's say a savings account, that earns, let's say, 5% interest a year. If you put in $1, it's a lot of money to some people, and you leave it alone, you come back a year later, how much money do you have if it earned 5%? How much money did you earn over the year at 5%? $1 at 5%. A nickel. Very good. Who said that? No one? You would earn a nickel, right? What's 5% of 100? 5. So, there you go. You earned a nickel for doing absolutely nothing. That's awesome, right? But what if you put in $100 at 5% and you left it alone for a year? You come back a year later, you have $5. $5 is more than a nickel, right? So the more you have, the more you get. Does money qualify? Yes, money grows exponentially in that circumstance. What else? What else grows fast? Rumors. Uh-oh. Rumors. That's not very Rachel's Challenge like of y'all to be spreading rumors. Do rumors grow exponentially? The more people you have telling the rumor, the faster the rumor's going to spread? Yeah, kind of like weeds, right? Kind of like weeds. So there you go. The more you have, the more you get. The less you have, the less you lose. So what about something that decays exponentially? Decay means decrease. But it sounds like more Halloweenish when you say decay. What decays exponentially? Baby diapers on the side of the road? No, those don't decay exponentially at all, right? They're kind of notorious for being around and not decaying. So that's why they don't want you to throw baby diapers on the side of the road. Chemistry. Uranium, very good. Uranium. All of your non-stable isotopes have something called what lives? Half-lives. And the whole idea behind a half-life is it takes that long to lose half of the amount. So the less you have, the less you lose, and the more you have, the more you lose, right? If you start with 100 grams, then whatever the half-life is, you've lost half of 100, which is 50. Then you're going to lose in the same span of time from 50 to 25. So you lost 50 the first time and only 25 the second time. So that is, the less you have, the less you lose, or the more you have, the more you lose. That's exponential. So exponential decay would be any kind of radioactive isotope that's not stable, that decays. Okay, cool. Uranium, I like that one. So we didn't list the things, but we wrote them down. List some real things. Well, let's write it down. Let's go ahead and write it down. Money, cha-ching, uranium. What else do we say? Rumors, weeds, and baby diapers? No, baby diapers is not on the list. I don't think they decay at all, not even like polynomialishly. Now, that was the intuitive definition. It grows at a rate proportional to the current amount. Here's the actual definition. An exponential function of the form f of x equals a times b to the x. So this a is the same a from the standard transformation form. It's your vertical dilation factor. It's also going to be your initial amount. So notice what makes it exponential now is you have a variable x in the exponent. The variable is the exponent, not the base. The base is a constant. So a can't be 0, otherwise you have the x-axis. A could be any number, but the value of the base b could be one of two things, or in two intervals. It could be either greater than 1, like 2, 3, 4, 5, 6. That would be exponential growth. Like cell division, right? Mitosis or meiosis, whichever one you want to talk about. What happens in mitosis? One cell cleaves and becomes 2. 2 then becomes 4. 4 becomes 8. 8 becomes 16. What's happening to the number of cells every cycle? They're doubling. That would be something that is purely exponential, base 2. The base would be 2. It would be 2 to the x, right? Double, double, times 2, times 2, times 2. If it's between 0 and 1, like 1/2, 2/3, this is exponential decay. All right, so e to the x would be our parent function for all of these exponential growth and decay functions. So if it's in this form, it's exponential. We call b the base. I've already kind of been alluding to that. We call b the base, where b is an element of, what is that? I think that's a misprint. B is, it looks like a degree bubble, right? B is an element of the real numbers, as long as it is greater than 1 or between 0 and 1. You can't have a base of 0 and you can't have a base of 1. Because if your base is 0, then you just get the x-axis. If the base is 1, you just get the line y equals 1. And if the base is negative, it breaks. Okay, you can't have a negative base. A is called the vertical dilation factor, but it's also called the initial value. When we say initial value, that kind of implies applications of this model. What value of time then usually corresponds with initially? 0, right? So if we were letting t be the independent variable instead of x, initial value corresponds with t equals 0. In this case, x equals 0. What do you get when you plug in a 0 for x? What's b to the 0th power? 1 to the 0 power, 2 to the 0 power is 1. So 1 times a is a. So that's why it's going to be the initial amount. It's your starting amount. If you have an application, you have to have a first seeding value for something to get bigger. You can't just go to the bank and deposit $0 and come back a year later and expect to have made a nickel, right? You have to put something in. You have to have a seeding value. Bacteria grow exponentially, right? Not good if you have an infection. You have to have an original amount of bacteria before it starts to grow. Even with uranium decay, you have to have an initial sample. Okay, so that initial sample is going to be what we call A. It's the y-intercept of the graph. It's the initial value of the function, and it's also your vertical dilation factor. Okay, so it stands for a lot of different things in a lot of different contexts. All right, we've already talked about what would happen if b was 1 less than 0 or a was 0. Here are some examples of some exponential functions. F of x equals 3 to the x power. The base is what? 3, and the exponent is x. Would this be growth or decay? It'd be growth, right? This would be something that triples every cycle. Every integer value of x, 1, 2, 3, 4, 5, you would get another factor of 3, okay? Times 3 times 3 times 3. So this would be growth. Here's another one, 2 times 10 to the x. Is that the same as 20 to the x? No, your dear Aunt Sally says to do exponentiation before you do multiplication, right? So this one would just be 2 times 10 to the x. 2 is the initial value, and then 10 would be the base. So this is something that's increasing by a factor of 10 each cycle. Okay, that's pretty rapid. But you're starting with 2. So this would be exponential growth. 4 times 1/2 to the x. This starts off with a base of 1/2. So what happens if you increase x by an integer value? 1/2 to the first is 1/2. 1/2 to the second is 1/4. 1/2 to the third is 1/8. What's happening there? 1/2, 1/4, 1/8, 1/16, 1/32, 64. Getting smaller and smaller. That's decay. Yeah. It's a decreasing function. We say it's decay. Decay, decrease. Pretty easy to remember, right? Decay, decrease. But we do know it's exponential because the exponent is a what? It rhymes with variable. Variable. Good. Whenever your exponent is a variable and your base is a number, it's going to be exponential. If you flipped it around and you said it was x to the 1/2 power, that's now a power function. That's the square root of x. Okay? So we flip it for the exponential. That's a power function, we call it. Where the base is a variable and the power is a number. Okay, cool. And of course, we have our old friend, Mr. f of x equals e to the x. He is the Papa Bear function for all exponential growth and all exponential decay of any base. You can always write them as a power of e. You'll see that as we move through the lesson. Okay, example 2. Now that we know what they look like, we're going to determine if each of the following is exponential. We'll put an e for an exponential, or not exponential, we'll put an n. So e if it is, n if it's not. Letter A, f of x equals 7 to the power of x. E or n? E, good, it's exponential. The base is 7, it's exponential growth. Letter B, x to the 7. That's not exponential. That's flipped around. The base is the variable and the power is the constant. It has to be the other way around. So that's a polynomial. Now that grows pretty fast for large values of x. Don't get me wrong. But 7 to the x grows a lot faster for large values of x. What about x to the x? Exponential? We have the variable and the exponent like we need, but we also need what as the base? A number, right? A number bigger than 1 or a number between 0 and 1. X is not a number. So this is a hybrid. This is a hybrid polynomial, hybrid exponential. This is not an exponential. This belongs to a family of functions called the Aleph functions. And they actually grow a lot faster than exponential when you have both the base and the exponent being variables. They grow pretty rapidly. Aleph, anyone know what Aleph is? Where that comes from? Not from France, but from... Anyone know the Hebrew alphabet? Well, if you did know the Hebrew alphabet, the first letter in the Hebrew alphabet, if you were reciting it, would be Aleph. There you go. Okay, how about this one? Exponential, yes or no? It looks like a transformation of an exponential function, right? The base is 15, and your exponent is a variable. It's shifted to the left one, but that's cool. And the -2 would be your a value. So that would take the growth function of 15, reflect it across the x-axis, stretch it by a factor of 2, and then move it left 1 unit. Okay? So that is an exponential function. 4 pi to the x. Exponential? Yes, it is exponential. What's the base? Pi or 4 pi? It was right. It was pi. Yeah, 4 is the a value. That's your vertical dilation factor. That's your initial value. Pi is the base. If you wanted the base to be 4 pi, guess what you'd have to have there? Parentheses. That would make the base 4 pi. But without the parentheses, you got to follow your dear Aunt Sally's rules, right? Exponentiate first, that's the pi, and then multiplication. So that is exponential. All right, the bottom row, 3 times 1 to the power of x. Exponential, yes or no? It has the variable in the exponent, and it has the numeric base. If you were to plug in different values of x, what would you get? 1 squared is 1. 1 cubed is 1. 1 to the fourth is 1. And all those times 3 is 3. Guess what this graph is going to look like? It's going to look like the line y equals 3. Is that exponential? That doesn't grow at all. Nope, this is not exponential. Even though it kind of looks exponential, this is not exponential. Remember, your base has to be strictly greater than 1 or between 0 and 1. It can't be 0, can't be 1, can't be negative. Can't be 0, can't be 1, can't be negative. Is this one exponential then? It is exponential. What's the base? 3. What's the a value? -1. Very good. If you wanted the base to be -3, guess what you'd have to have there? Parentheses. And then that still wouldn't be exponential. If you try to graph that on your graphing calculator, you might want to put some safety goggles on before you hit graph, because it's going to break. All right? Because it's trying to raise -3 to real numbers, not just integer numbers, but to real numbers, and it will not be exponential. So you got to be careful, right? You got to read the language. If there is no exponent, the base is the thing that is immediately attached to the 3. Now, if we write it like this, 15 to the x, you know that the base is 15 and not 5, right? That's not 1 times 5, that's 15. But if it's a combination of like a negative or a variable, then it works. All right, letter H. Is that exponential? No, it's not. That's not, because the base is negative. The base is negative, and you can't have a negative base on an exponential function. 0 to the x. That's also not exponential. That's just 0. Everywhere except at 0. That's the x-axis minus the origin. That's not exponential. Can't have a base of 0, can't have a base of 1, or negative. How about this dude? If we kind of rewrite it slightly, that's the same as 3 times 4 to the what power? Positive x, right? We've studied the rules of exponents. If you have a negative exponent at the bottom, bring it to the other side, it's positive. So it's kind of the same function as 3 times 4 to the x. Is that exponential? Yes, it certainly is. Yep. Very good. All right, so now it says calculator time. Evaluate the following. Calculator? We don't need a calculator, do we? Let me show you what it looks like on the calculator. If you want to grab a calculator, that might be more work than is needed. But certainly you can use one if you have it with you. We have the function 1/3 to the x. Is that going to be exponential growth or decay? That's going to be decay. Very good, because the base is 1/3, which is less than 1. We want to evaluate f of 2. So I'm going to go ahead and plug it in. F of 2 is going to equal 1/3 to the 2th power. And of course, we could simplify that. What's 1/3 times 1/3? 1/9. All right, there's your answer. 1/9. We don't need a calculator. If you wanted the decimal, you could. F to the -3/4. Well, we plug that in, we get 1/3 to the -3/4. Are we allowed to have negative exponents? Sure, yeah, we just can't have negative bases. So that one, let's see how far we can go without the calculator, and then we'll go to the calculator. What if I wanted to get rid of the negative? What would I do? Put it under? We all did this in kind of intuitively at the beginning of the year. If you have a fraction raised to the negative power, all you got to do is flip the fraction and change the sign of the exponent, right? So if you flip 1/3, you get 3. That's the same as 3 to the +3/4. Now that's the same as the 4th root of 3, which is not a nice number, cubed, or the 4th root of 3 cubed. What's 3 cubed? 27. Yeah. Now, if you want to know what the 4th root of 27 is, here's one way you can evaluate this. Let's finish going without the calculator, and then I'll come back through. F of pi, that's just going to be 1/3 to the pi-th power. Can the exponent be a non-integer? Yeah, the exponent can be any real number. So I'm not sure what that is. And f of the square root of 2, that's 1/3 to the square root of 2's power. Now, if you wanted to evaluate all these as decimals, you can certainly type in 1 divided by 9, 27 to the 1/4 power, 1/3 to the pi-th power. But here's another way to do it on your calculator. Pretty cool. If you go to y1, and you type in 1/3 to the x power. So I'll type it in with parentheses. Using math print, the n over d, that's the horizontal division bar, 1/3, close parentheses, and then raise it to the x power. If you hit zoom 6, that's your standard viewing window, you'll see an exponential decay function. Now you can just hit the trace button and type in your values. What was the value at 2? Well, type in a 2. You get 1/9. We already knew that. Here's the way to do it from the home screen. If you want to know what the function value was at 2, just recall it from y1. Alpha trace, that's your F4 menu. It has all of your y's. We put ours in y1, so if I hit enter, there it is. And now if I just open parentheses, put in my 2 and close parentheses, your calculator acknowledges that as evaluating the function at 2. You hit enter, and you get 1/9. Now I'm getting the nice fraction of 1/9 because I am in pretty print, I think. Fraction type, answers auto. If you want the decimal version every time, you can come down here to your answers, change it to decimal, and then you could do it again. Second enter recalls. Well, now if you hit enter again, nope. I guess you have to go 1 divided by 9. There it is. So that ends up being 0.111. How many decimals should we report if it doesn't terminate? You should get in the habit of always reporting 3 decimals, rounded or truncated. Okay, so now f of -3/4, back to the calculator. We know it's going to be 4 through to 27, but you could just do that again. Alpha trace, number 1, and then just type in a -3 divided by 4. And that gives you 2 point, how many decimals? 3. So either 279 if you truncate. Truncate means chop off, not round. Or if you round, 2.280. If you did round, you would need that third decimal as a 0. It's part of the accuracy. It's not just a trailing 0. What is f of pi? Well, now you can just hit second enter. Come back here, get rid of the -3/4, and just type in a pi, which is second caret. And you get that number there, 0.031 or 0.032. And then finally, f of the square root of 2, again, just hit alpha trace, number 1, open parentheses, square root of 2, close parentheses. It treats that like function evaluation, just like f of the square root of 2. And you get the decimal 0.211. All right, so there's a little bit of calculator work for us. Now it says, example 4, create a table of values for 2 to the x and 1/2 to the x on the same axis. We're going to graph them. What do you notice about them? Okay, let's go ahead and just go straight to the graphs. So what we're going to do here is on the same set of axes, we're going to graph 2 to the x and 1/2 to the x, and we're going to see if there's a relation between them. So I'll use this blue color for 2 to the x. Let's just kind of generate some points and plot them as we go. Let's try x equals 0 on the y-axis. What's 2 to the 0 power? 1. So I'll just put a 1 right there and put a dot. Let's plug in a 1. What's 2 to the first? 2, right? There's 2 points. If we connect them now, we get a straight line. Is that what we should do? No. Let's go out here to 2. What's 2 squared? 4. So notice it jumped up there a little bit higher. And if we go out 1 more to 3, that's 2 cubed. That's going to be what? 8. So we have to go even higher now, way up here. 2 cubed is 8. So there we have 4 ordered pairs so far. Let's go backwards. -1. What's 2 to the negative first? Off to the side here. 2 to the negative first is 1 over 2 to the positive first, right? Remember that? So that's 1/2. So at -1 we have a half. That's going to be right there. At -2, what's 2 to the negative second? That's 1 over 2 to the positive second. That's 1 over 2 squared. That's 1/3. fourth, right? That's even closer to the x-axis. And one more, -3. 2 to the -3 is 1/8. That's even closer. So you're going to kind of lose the ability to draw a value that's closer to the x-axis without putting it on the x-axis. Now you can see kind of what the points are doing. If you connect the dots, it's going to come like this and look like that. So there's the graph. It's exponential growth. It looks a lot like e to the x. The only difference is e to the x is going to be a little bit steeper than this because e is 2.7, so it grows a little faster than just plain old 2. All right, now I'm going to pick a nice contrasting flavor like red. And we want to, oops, I should put f of x there, not f of 2. There we go, f of x. All right, so now we're going to sketch f of x equals 1/2 to the x. And because 1/2 is less than 1, that should be decay. Let's do the same points. What is 1/2 to the 0 power? It's 1. Very good. If you plug in a 1, what's 1/2 to the first? It's a half, right? Plug in your 2. That's 1/2 squared. That should be 1/4. And if you plug in your 3, you get 1/8. So notice the exact same y values we got on the negative side of 2 to the x, we're now getting on the positive side of 1/2 to the x. And if we work backwards, 1/2 to the negative first, what's 1/2 to the negative first? 2, right? So that's going to be right here. If you plug in a -2, what's 1/2 to the negative second? 4. And of course, if you plug in the -3, 1/2 to the negative third is +8. Notice the same thing happened. All of the positive y values for 2 to the x, we now kind of flip them over the y-axis. In fact, if you wanted to get from one of these graphs to the other, that's all you'd have to do. These graphs are reflections of each other across the y-axis. And so that's going to be true of any exponential function of the form b to the x and 1 over b to the x. They're going to be reflections of each other across the y-axis, the growth and decay pairs, if you want to think of them that way. Now, we can actually prove that. Watch this. If we take 1/2 to the x, let's go ahead and use our rule of exponents. I can write that as 1/2, that's 2 to the negative first, right? 2 to the negative first times or raised to the x power. Now what do we do with the exponents when we're raising a power to the power? You don't add them, you multiply them. So -1 times x, you just get 2 to the negative x power. Ah, there you go. So 1/2 to the x is the same as 2 to the negative x power. What transformation does that give us when we replace x with negative x to any function? It's a reflection across the y-axis. Yep, there you go. So we just proved it through the equation. It would work the same then with 1/3 and 3, 2/3 and 3/2. As long as the bases are reciprocals of each other, those graphs are going to be reflections of each other across the y-axis. Okay? So here is kind of a nice little picture of some exponential growth functions and their reflective decay partners. So let's look at the growth functions first. If you look for positive x values, the slowest growing one is 2 to the x. The next fastest growing one is 3 to the x. Then the blue one is 5 to the x. And then finally 10 to the x. So if you notice here, let's kind of make a statement. If the base, when the base is bigger than 1, in other words, if we have growth functions, the blanker the base, the blanker the graph. What can you say? Well, let me throw it in there for one of those. The bigger the base. How about that? The bigger the base, what could you say about the graph? The faster it grows, right? You can also say that the graph is, what's her? Steeper. That's a good word. The bigger the base, the steeper the graph. And it's steep on both sides. So if you notice 2 to the x is pretty slow growing to the right, and it's also pretty slow going to the x-axis on the left. Whereas 3 to the x is pretty fast going to infinity, and it's a little bit faster going to 0. So the graph is steeper on both sides. So for exponential growth, the bigger the base, the steeper the graph in both directions. Notice they all pass through what common point right here? 0, 1, right? 0, 1, they all have the same y-intercept. Let's look at what happens over here on the decay side. The slowest growing function, or the slowest decaying function, is 1/2 to the x. A little bit steeper is 1/3 to the x. A little steeper than that is 1/5 to the x. A little bit steeper is 1/10 to the x. So on the other side here, if your base is between 0 and 1, then the blanker the base, the blanker the graph. Let's fill in one of those so we can compare it to the other one. Let's keep the word steeper in there. The blanker the base, the steeper the graph. Over here it was the bigger the base, the steeper the graph. Now 1/10 is the steepest shown. How is 1/10 compared to 1/5? Bigger or smaller? Smaller, right? So it's kind of the inverse over here, or the reciprocal effect. The smaller the base, the steeper the graph. It's the opposite for decay. Where would e to the x fit in over here for exponential growth? Between the pink, black, blue, and purple. Where would it fit in? Between the pink and black. Very good. Let's draw him in there, our parent function. So come out here. I'm choosing beefy brown. I'm going to come in right there and say that that's equal to y equals e to the x. And now, when I come through the other side, since it's between the pink and the black one, I got to make sure it stays between the pink and the black over here. There we go. So there's your parent function. So within each family of functions, you have certain functions that grow faster than others. Just like in the polynomials, x cubed grows faster than x squared. X to the 5th grows faster than x to the 4th. Same thing here with growth and decay. The bigger the base for growth, the steeper the graph. For decay, the smaller the base, the steeper the graph. All right, and it makes for some pretty artwork as well. But notice all of the ones that are just reciprocals, 10 and 1/10, 5 and 1/5, 3 and 1/3, 2 and 1/2. They're just reflections of each other across the line y, x equals 0, the y-axis. Okay, so that's all kind of algebra 2 type stuff. Let's go ahead and look at the parent function again. This should be a review. We're going to graph parent functions now using our transformations. So we're going to revisit our parent function e to the x. He's the granddaddy of all exponential growth and decay functions. So this is the one that was on the test, right? We practiced with logs, logs, logs. We practiced a little bit with e's. And just like I promised, there was an e function on the test yesterday. Some people were drawing the e functions with vertical asymptotes. That's not real good. Which reminds me, real quickly here, if you have y equals the natural log of x, if you write the natural log of x without script letters, the L in natural log sure looks a whole heck of a lot like a what? A vertical line, right? So guess what type of asymptote natural log of x has? Vertical. And e to the x, its inverse, if you draw e like this, ooh, I got carried away there. My bad. Then the tail on the e sure looks a whole lot like a what? Horizontal asymptote. So if you're still getting those confused, you need to fix that. So e to the x, there it is. It's the horizontal asymptote. It's exponential growth, so it comes in like that. And we just drew it up above. When you're drawing them by themselves, you don't have to worry about how steep you're making it. But if you draw more than one exponential growth function on the same axes, now comparatively, one has to be steeper than the other. All right, so for e to the x, it passes through the point 1, 0. Let's just kind of go through the whole gamut of things again. The domain of this function is what? All real numbers. Some people missed that on the test yesterday. The range of this function is everything strictly greater than 0. So you could say 0 to infinity, like that, or the set of all y's such that y is greater than 0. Does it have any symmetry? No, no symmetry. We already found the y-intercept is 0, 1. Is it monotonic or strictly increasing or decreasing? Yep, it's monotonic, if you want to say monotonic, or you could say strictly, it doesn't matter. It's strictly increasing, INC. Is it 1-to-1? Remember that additional property we talked about? A function is 1-to-1 if its graph passes the what test? The Precal test? The horizontal line test, yeah. And this one does. So this one is also 1-to-1. Let's go ahead and say this also. It is also continuous for all x. That's nice. It's a continuous function. So anytime you have a continuous function that's monotonic over its domain, it's going to be 1-to-1. And then the end behavior. Some people miss this too. The limit as x goes to infinity of e to the x, and the limit as x goes to negative infinity of e to the x. You can certainly look at the graph, right? The right end behavior is infinity, the left end behavior is 0. But you can also get it by plugging in. Here's what I mean. E is, remember, like 2.7, almost 3. What happens when you raise it to larger and larger powers? E to the first, e to the second, e to the third, e to the hundredth, e to the millionth, e to the zillionth. What's happening with those numbers? They're getting really, really big, really fast. That's approaching infinity. You don't even need the graph. What happens if you're approaching negative infinity? Well, plug in negative numbers. E to the negative first is 1 over e. E to the negative 10th is 1 over e to the 10th. E to the negative a millionth is 1 over e to the millionth. What's happening with those values? They're approaching 0, right? 1 over, if you have 1 over something that's growing really, really fast, 1 over infinity is essentially 0. 1 over something that goes to infinity is approaching 0. So guess how infinity and 0 are really related? They're reciprocals. Infinity and 0, for the most part, are reciprocals of each other. What's the reciprocal of a really, really small number close to 0? A really, really big number approaching infinity. What's the reciprocal of a really, really big number approaching infinity? A really, really small number approaching 0. All right. Anything else you want to say about this guy? He's smooth. Let's say that. He's smooth. With a couple of extra O's. Smooth. All right. When we get into calculus next year, we'll talk about smoothness being a characteristic of a graph. There's no jagged edges or jagged points. We say it's differentiable. Okay? And this one is pretty smooth. It's not just continuous, it's smooth. What would a graph look like if it was continuous but not smooth? Very good, absolutely. The absolute value of x is a graph that's continuous, but it's not smooth everywhere, because there's a sharp turn right there. Not smooth. Okay, sweet. How are we doing so far? Kind of fast, but kind of easy. Haven't really done anything. Example 6. Oh, this should be a piece of cake. The reason we're doing these again, even though we tested over this yesterday, is because, remember, we're skipping chapter 3. So with the mindset that we've had a whole other chapter between the test over this, we could probably skip that, but I'm not going to. Let's just sketch it real quickly here, because some people were still missing this on the test. In standard transformation form, that looks like that. The negative in the front is your A value, the plus 3 is the D value, and the minus 1 is the C value. So let's see if we can go straight to the final graph. You should be able to do this in your head. You have an idea of what e to the x looks like, right? Exponential growth. The negative in the front is going to reflect it across the x-axis. So it's going to be decreasing below the x-axis. The minus 1 shifts it right 1. We don't really show that. The plus 3 moves it up 3. So now we go to 3. And because my graph is going to live below, it's going to look like this. More than likely. But there's one thing we have to check, right? Depending on how steep it is, it could actually start going towards negative infinity a lot sooner and cross the y-axis in negative land. So just as an added precaution, let's figure out what f of 0 is. It's 3 minus e to the negative first. That's the same as 3 minus 1 over e. 1 over e is about a third, right? What's 3 minus a third, positive or negative? Should be positive, right? So is my graph okay to leave it like that? I have it crossing in positive lane. Yeah. So the domain of this is all real numbers all day long. And the range of this guy is everything strictly less than 3. Do we have a horizontal asymptote? Yeah, we have a horizontal asymptote at y equals 3. What is the limit as x goes to negative infinity of this function? 3. Those are like the last 3 questions on the test yesterday. They were all the same number, right? The range, the horizontal asymptote, and the one-sided limit. They all have the same value associated with them, 3. What would be the limit as x goes to positive infinity? Negative infinity. Now let's say we didn't know if our graph was right. How can we figure that out? Well, let's plug it in here. Infinity is not a number, so you can't really plug in infinity per se, but you can think about it. What's infinity minus 1? Tee-hee-hee. Infinity, right. What's e to the infinite power? Infinity. What's 3 minus infinity? What kind of infinity? Negative infinity, right? And so that's the answer here. You don't really need the graph. For n behaviors, you can always analyze what's happening to the function as x gets really, really big towards infinity or really, really small towards negative infinity. All right, so here's one that's a little bit better or different. Now we're sketching this guy. What is the parent function here? Is it exponential? It is. You can tell it's exponential because it has a variable exponent and the base is 7. So the parent function is 7 to the x. That's the parent function. Is that growth or decay? It's growth. So it's going to look a lot like e to the x. The only difference is, compared to e to the x, it's a little bit whatter? Steeper, okay? But remember, if we're only sketching one function, we don't have to really show the steepness. It's only when we compare two on the same graph we show the relative steepness. So we're going to pretend, essentially, that this is e to the x. So to sketch this one, we got a negative 3 times 7 to the negative parentheses x minus 5 plus 4. There it is in one fell swoop. The exponent, if you flip it around, you get negative x plus 5. You factor out the negative from both terms, and you get negative quantity x minus 5. Now I'm going to see if we can graph this guy in one step, like we just did for the e function. So our parent function, we do have something to reference. It's like e to the x. The 3 is going to make it steeper vertically by a factor of 3. That's great and all, but we don't show that. We have a reflection both across the x-axis and the y-axis, yes? Across both. It doesn't matter the order. If you want to reflect it across the y-axis first, it looks like that. Then you flip that one across and it looks like that. So we're going to have a function that is increasing below the x-axis, right? It's going to be an increasing function from left to right below the asymptote, which gets moved up to 4. So now if you draw your increasing function, it's going to look something like that. And once again, depending on the steepness or if we're shifting it left or right, that graph may have a negative y-intercept or a positive y-intercept. We better figure out which one it is. So let's go off to the side and show f of 0. F of 0, when you plug it into the original one, which is a little bit easier, is 4 minus 3 times 7 to the 5th power. 7 to the 5th power is kind of big, isn't it? Times a 3 makes it even kind of bigger. It's certainly going to be bigger than 4, right? So 4 minus a big number is positive or negative? Negative. How's my graph? Not so good. I have it crossing in positive land. So because we shifted it right 5, look what happens if you grab that with your scissors and you just scoot it right an approximate 5. That essentially moves the y-intercept. So it is a negative y-intercept. And there you go. What's the domain? All real numbers. What's the range? Everything strictly below 4. So if you want an interval notation, that's negative infinity to 4 with a what? Bracket or parentheses? Parentheses. Yeah, very cool. Very cool. All right, we'll stop right there for today. That's example 7. We got pretty far into these notes. We haven't really done anything new yet. We'll pick up with something more interesting tomorrow on example 8. But you do get your test tomorrow, and we'll talk about it briefly and talk about when the retest is. So there you go. Good start on exponentials.